Okay, 13.2 and 13.3, we're going to start by talking about saturated, unsaturated, and supersaturated solution. In a saturated solution, you have dissolved as much of the stuff into the water as you possibly can, and you pour any more in there, it is just going to sit there at the bottom. And y'all guys have seen this before. If you take some sugar, you pour it into some tea, you keep pouring it in, pour it in until the tea is so sweet can't hold any more sugar. We call that a saturated solution. In an unsaturated solution, you just put a little bit of sugar in there and dissolved it, and if you wanted to, it could hold some more. That's an unsaturated solution. Now, something that's super cool are supersaturated solutions. You have actually seen a supersaturated solution before when we used those hand warmers, that sodium acetate solution. That was a supersaturated solution. What we did there was we had a solution that had dissolved more sodium acetate than was possible. The way we do that is we heat it up really, really hot. We go ahead and dissolve a lot more into this than it can normally hold. So a lot more sodium acetate into water than it can normally hold. We cool it down really slowly. And if we cool it down real slowly, it will stay dissolved in the liquid. And then all you have to do, and this is cool, there's a picture of this on page 536, and this is what happened with our hand warmers too. All you have to do is provide a little point for it to reform around, and it will very quickly reform around that point and will release a lot of heat, make a very exothermic reaction when it does that. Things that can affect solubility. First off, there are the solute-solvent interactions. So the interactions between your solute, like your Na, your Cl, whatever, and your solvent, like your water. The stronger your attractions are there, the more likely it is that it's going to dissolve, all right? And so the greater the solubility. So if you have a great attraction for those Na ions to water, or a great attraction to those Cl ions to water, then you're going to have high solubility. If these attractive forces here aren't very strong, then it's probably not going to dissolve very much. You can dissolve gases into liquids, like when you drink a Coke, that's carbon dioxide that has been dissolved into that liquid. Gases are mostly affected by London dispersion forces, so the stronger those London dispersion forces are, then the stronger those bonds are between the gas molecules and the water molecules, and the more soluble it is. And remember, London dispersion forces are all caused by moving electrons. The more electrons you have, the greater the London dispersion force, so the greater these attractive forces are going to be. Another way of saying this, the larger the gas molecule, or the more electrons the gas molecule has, the greater the London dispersion forces are going to be. And so, as your molar mass of your gas goes up, solubility is generally going to increase. Generally. Not always, but generally. So if we look at this question here, between N2CO and Kr, which one's going to have the highest solubility? Well, it's the one that's going to have the largest molar mass, which is going to be krypton. Don't forget to multiply this times 2. This is 2 times 14. That's going to be 28. And then the rest of them you can just look on the periodic table and figure out. Two terms you need to be sure that you know: miscible and immiscible. Miscible just means that they're going to dissolve completely into one another. Immiscible means they're not going to dissolve into one another. The most common and popular way to describe whether something's going to be miscible or immiscible is that thing right there: likes dissolve likes. That means polar molecules tend to dissolve other polar molecules, and nonpolar tend to dissolve other nonpolar molecules. So if you take water, which is polar, and oil, which is nonpolar, try to mix them together, they're not going to mix. You got an immiscible substance because they are not like one another. You need to be able to predict whether or not something will dissolve into something else. So most of the time they're going to give you something like, will this dissolve in water? For ionic compounds, you just memorize your solubility rules. But for other things, things that are good, that might be good to know, most hydrocarbons tend to be nonpolar. Alcohols, however, tend to be polar, and since they're polar, they're probably going to dissolve in water. In general, for alcohols, when you tend to have really, really long carbon chains, you increase the length of these carbon chains here, they tend to become less and less polar, and so that means they become less and less soluble. All right, and so when you get short carbon chains, they tend to be more polar than the longer ones. So for this molecule here, this is glucose, the question asks, why is this very soluble in water? It's not really the carbon chains that are causing this to be that's causing it to be soluble in water. It's these guys right here, right? Look at all of these alcohol chains, all right, and this double bonded oxygen over here. This makes this thing super polar. All right, this is not a nice symmetrical molecule. This is an incredibly polar molecule, even though it's a hydrocarbon, and that makes it be able to dissolve in water. For gases, there's a couple things that can determine how much they will dissolve in water. One of the things is pressure. Henry's law tells us that the amount of gas dissolved in solution is directly proportional to the pressure of the gas above the solution. This means that if you take a gas and you pressurize it into a solution, you can make the solution dissolve more of the gas, right? Which is why Coke cans and things like that are pressurized, because they're holding gas. If you open a Coke can, it's going to depressurize. And when it depressurizes, what happens here, and this is the question I'm explaining right here, what is CO2 extra your soft drink when you open it? When you open your Coke can and you depressurize it, what happens is you reduce the amount of pressure above the gas, and that makes, above the solution, and that makes the gas less soluble in the solution. And so since the gas is less soluble, then it's going to lose a lot of it. It doesn't lose all of it, which is why it's so fizzy, but it loses a lot of it. The equation that you can use to figure this out is this equation right here. The P stands for the partial pressure of the gaseous solute above the solution. C is concentration of dissolved gas, or molarity. In fact, a lot of times you'll see it written like this instead, which makes a lot more sense. And then K is a constant that is characteristic for a particular solution. And there's a lot of different versions of Henry's law. In fact, this is the one that's in your textbook. There's a ton of different ways that this is written. The best thing to do is to take a look at what they give you for K, and then just use dimensional analysis, try to cancel out your units to get your pressure in whatever units it's given you in ATM, kPa, whatever, or sometimes it'll ask you to solve for moles or something like that. This equation is not one that shows up very often, but it does show up every now and then. For solids, increasing temperature is always going to cause the substance to dissolve more rapidly. Whoops, I just wrote the wrong word. I meant more rapidly for solids. Increase in temperature will usually increase the solubility. But not always, which is really weird. Most of the time it's going to do that, but if you look over here, if you look at this chart right here, okay, most of the time for most of these substances, right here, as temperature goes up, as solubility is going up too. But look at this guy right here. Really strange. As the temperature went up, its solubility actually went down. And so there are a few solids that that's not true for, but most of the time, as you increase temperature, you increase solubility. And all of the time, as you increase temperature, it will dissolve more rapidly. Now for gases, it is the opposite. For gases, solubility always decreases whenever you increase temperature. Look over here at this chart. All right, as you increase your temperature, your solubility actually goes down. Look at that CO2 line right there. All right, and that makes sense. We know that. If you take a open can of Dr. Pepper, you put it in the fridge, or an open can of Dr. Pepper, and you put it out on the counter, the one on the counter is going to go flat a lot faster, because when it's warmer, its solubility goes down. That means that it'll hold less CO2. It means it's going to go flat. When it's colder, it can hold more CO2, so it's not going to go flat as fast.